Hey everyone, and welcome to this explainer. Today we are going on a seriously fascinating journey to the absolute edges of the universe. But more importantly, we're going to the edges of our mathematical models. We're going to explore exactly what happens when we push matter and the physics equations that describe it to their most extreme physical conditions. We'll see how our nice, neat, orderly formulas completely break down under crushing gravity or freezing temperatures, and how physicists have had to conceptually derive entirely new math just to save the day.
Okay, let's dive into this. We've got a really structured journey mapped out today, starting with normal thermodynamics and going all the way to extreme gravitational and quantum physics. Our stops are the ideal gas illusion, deriving the real world, gravity versus the atom, the math of neutron stars, approaching absolute zero, and finally, when resistance becomes zero. Starting right off with Section 1, the ideal gas illusion, a flawless mathematical world. So in standard physics, the baseline formula for a perfect world, how gases behave, is the ideal gas law. You've probably seen it. PV equals nRT. Pressure times volume equals the number of moles times a constant times temperature. Honestly, it's a beautiful, elegant equation, but it relies on a massive assumption. It imagines that gas molecules are perfect, infinitely tiny point particles that never, ever interact. Think of it like a one-hour football match where no players ever consume energy and absolutely no players ever collide with one another. It's a perfect condition, but in the real world, it's impossible. Real gas molecules occupy physical, finite space. And as they zip around, they pull and push on each other. When a molecule is about to strike the wall of a container, the other molecules behind it actually pull it back slightly, which fundamentally alters the actual pressure.
Which brings us to Section 2, deriving the real world, fixing the equation.
Because of those messy, real-world collisions and attractions at high pressures and low temperatures, our beautiful PV equals nRT equation just completely fails. It breaks down. So a brilliant scientist named Johannes Dieterich van der Waals stepped in to conceptually derive the real world step by step. He realized he needed to make two very logical corrections to the math. First up, the volume correction. Imagine 30 students in a classroom. Those students take up actual physical space, meaning the empty volume left for them to move around in is less than the total volume of the room, right? So mathematically, van der Waals subtracted this excluded space, giving us the term V minus NB. Second, the pressure correction. Because molecules attract each other, a molecule hits the container wall with less force than it would if it were totally alone. To find the true ideal pressure, we have to conceptually add back that lost pressure. This gives us P plus A times N squared over V squared, where that A simply represents the strength of the intermolecular attraction.
And this brilliantly illustrates how just a few logical corrections allow us to mathematically model gases under much wider ranges of pressure and temperature. We swap out the simple P and V with these derived corrections, and suddenly we have a mathematical model that actually works for real, sticky, complicated gases. Moving on to Section 3, gravity versus the atom, the extreme crush.
Okay, let's leave the tiny laboratory containers behind and zoom way out to the grand violent scale of stars. Out here, matter isn't just sticky, it's subjected to the absolute most extreme crushing forces in the universe. A normal star, just like our sun, survives because of a very delicate mathematical balance called hydrostatic equilibrium. It's a literal tug of war. Gravity is your inward force, ruthlessly pulling massive amounts of gas toward the center. Fighting against it is the outward force of incredible gas pressure and heat generated by nuclear fusion in the star's core. But here is the breaking point. When a star burns through all of its nuclear fuel, that outward fusion pressure simply drops to zero. With absolutely nothing left to fight it, gravity just takes over entirely.
Now, what's really interesting about this slide is how we can conceptually break down the math of this collapse. If we look at the fundamental formula, little g equals big G times mass divided by the radius squared. As a star's nuclear fuel dies, it collapses inward. That means its radius, r, shrinks drastically, but its mass, that remains astronomically huge. Mathematically, when you divide a massive number by an incredibly tiny, shrinking number squared, the result just spikes toward infinity. It becomes a completely unchecked, atom-crushing force of gravity.
Let's see what that crush does in Section 4, the math of neutron stars, squeezing the sun.
Under this infinite mathematical spike in gravity, normal atoms simply cannot survive. The extreme pressure literally forces the particles to mutate, creating what physicists call degenerate matter. When gravity squeezes atoms, the electrons are pushed intensely close to the nucleus. But quantum mechanics has a strict rule called the Pauli exclusion principle.
It basically states that no two identical particles can occupy the exact same quantum state. Think of it like two people trying to sit in the exact same physical chair at a crowded movie theater. It just doesn't work. Because they refuse to be squeezed any closer, these electrons violently resist, creating a new outward force called electron degeneracy pressure. Now, this is what stabilizes smaller collapsed stars, known as white dwarfs. But if the star's mass is massive enough, even the electrons lose this battle.
The gravity becomes so incredibly, unbearably intense that it completely overcomes the electron's resistance. The electrons are literally forced inside the nucleus and violently squashed together with protons. An electron and a proton are crushed to merge and become a pure neutron. The entire star becomes a giant, tightly packed ball of pure neutrons, held up only by neutron degeneracy pressure. It's an almost unimaginable level of physical violence.
And the mathematical result of this quantum crushing? It's staggering. A neutron star can possess 1.5 times the mass of our entire sun. But all of that matter is squeezed into a diameter of just 20 kilometers. That is an entire sun condensed into a sphere the size of a short drive across your city. No way, right?
To really grasp this extreme physics, let's look at the density. Because the mass is so huge and the volume is so tiny, just one single cubic meter of a neutron star would have a mass of 100 quintillion kilograms. That's a 1 with 20 zeros. If you had a spoonful of this degenerate matter here on Earth, its gravity would be so intensely concentrated that it would plunge straight through the crust all the way to the center of the planet.
Let's move to and see how this builds in Section 5, Approaching Absolute Zero, the Extreme Freeze. So, we've looked at the extreme limits of high pressure and gravity. But what happens to the math of matter when we go the other way? When we extract almost all the energy out of it and approach an extreme freeze? Well, when you plunge temperatures down to near absolute zero, which is negative 273.15 degrees Celsius, kinetic energy essentially just stops. At this point, we enter the fifth state of matter, the Bose-Einstein condensate. Predicted by Satyendranath Bose and Albert Einstein, something truly magical happens here. Individual particles lose their identities entirely. Instead of acting like a chaotic classroom of bouncing individuals, they all condense into the exact same quantum state, acting together as one giant unified superatom.
And this shared quantum state gives rise to absolutely mind-bending properties, like superfluidity. In normal fluids, like water or honey, the layers of the liquid experience friction as they slide past each other. This is called viscosity, and it means the fluid naturally loses energy as it moves. But if you supercool a fluid, like liquid helium, into a Bose-Einstein condensate, it becomes a superfluid. The friction between its internal layers drops to exactly zero. It has absolute zero viscosity. If you were to stir a cup of superfluid, it forms persistent vortices, little whirlpools that will spin infinitely, forever, without ever slowing down or losing a single drop of energy. It is genuinely breathtaking to think about.
This brings us to our final stop, Section 6, when resistance becomes zero, redefining Ohm's law.
So this unbelievable phenomenon of zero friction isn't just limited to physical liquids. It also applies to electricity, which fundamentally disrupts basic high school physics circuits. We all know Ohm's law, right? Voltage equals current times resistance, V equals IR. Usually, to increase the current, you have to increase the voltage or cool the wire to lower the resistance. But think about the mathematical limit here. What happens to this equation when resistance drops not just to a small number, but to exactly zero? What happens mathematically when we divide by zero? Well, the current becomes essentially infinite. It flows forever without any energy lost. This physical reality is called superconductivity. When certain materials are cooled below a specific critical temperature, their electrical resistance completely vanishes. Conceptually, this happens because electrons, which normally bounce around and scatter off things, causing electrical resistance, pair up into what are called Cooper pairs. Just like the unified particles in our supercooled superfluid, these Cooper pairs glide smoothly through the material's atomic lattice without a single collision. No friction, no loss of energy.
And this isn't just some wild mathematical theory. It was actually discovered over a century ago in a stunning laboratory realization. Back in 1911, the Dutch physicist Heike Kamerlingh Onnes was experimenting with liquid helium. He cooled solid mercury down to a mind-numbing 4.2 Kelvin. Suddenly, to his absolute shock, his instruments showed that the electrical resistance of the mercury hadn't just decreased, it had entirely inexplicably disappeared.
So the crucial point is, this extreme zero-resistance math is already quietly powering our modern world.
Because superconductors allow massive amounts of current to flow without burning up, they can generate incredibly powerful magnetic fields. We use them today in MRI machines at hospitals, which generate immense 32 Tesla magnetic fields to literally see inside the human body. They allow maglev trains to float silently above magnetic tracks, and they are absolutely the key to building the next generation of highly efficient power grids and lightning-fast computer chips.
We've traveled a really long way in this explainer. We've seen how physicists had to conceptually correct the ideal gas law to account for messy reality. We've watched the brutal math of gravity crush atoms to forge neutron stars the size of a city. And we've witnessed the bizarre, frictionless world that mathematically emerges near absolute zero. But physics is never truly finished. As we continue to probe the extreme edges of pressure, density, and temperature, we have to wonder, what new impossible equations are still waiting to be discovered at the absolute limits of our universe? Think about that next time you look up at the stars. Until next time, stay curious.